The last video talked about a particular example, among other things, of an affine variety X, which could be decomposed into union of irreducible subvarieties X1 and X2, which themselves can no longer be decomposed further. And in today's video, we want to understand this phenomenon more generally. And we can actually go to a pretty general setting and talk about topological spaces X, which have a property guaranteeing that we can find such a decomposition into irreducible subsets. And the right condition to look at here is that the topological space X should be Noetherian. And by definition, this means that there is no infinite strictly decreasing chain X0, X1, X2 of closed subsets of X. So the idea is whenever you start with any closed subset, X0, could be something like this, then you can look at chains of smaller and smaller closed subsets contained in there. So for example, here, you can get rid of the curve except for a single point. This would give you a closed subset, X1. And then in each step, you want to take a strict subset. So you need to get rid of something. So you could get rid of this point entirely. And then you could get rid of the last point, and then you're left with the empty set. In this case, this chain here would end. It cannot be extended further and further on the right. And so if such a infinite chain doesn't exist, then the space is called Noetherian. The first observation is that, again, the classical topology on Rn, for example, is disappointing in this regard, because Rn with the Euclidean topology is not Noetherian. So for this, you need to find such an infinite strict chain of closed subsets. And what turns out is that in algebraic geometry, this is a useful concept because any affine variety X with the Zariski topology happens to be a Noetherian topological space. And so for the proof, we assume, just by contradiction, let's assume that we had a decreasing chain X0, X1, and so on, as above. Then, well, we want to flee again into commutative algebra because there we already have a lot of results. So the way to do that is to take this chain of subsets and apply this inclusion reversing bijection by taking the vanishing ideal in the ring of functions on X. If we do that, then we get, when we define I0 to be the vanishing ideal of X0, and so on. And then these strict inclusions become strict inclusions in the other direction. So the fact that the orientation of the inclusion changes, this is this inclusion reversing part. And the fact that none of the strict inclusions becomes a non-strict inclusion, namely an equality, comes from the fact that this is a bijective map. Okay, so we have managed to get to the realm of commutative algebra, and we have gotten ourselves an infinite increasing chain of ideals in AX. And this hopefully starts ringing some bells, because now we have just a few observations. So firstly, we have complete control over AX. It's just a quotient of this polynomial ring by the ideal of the ambient affine variety X. And then, well, there was something about infinite increasing chains of ideals, namely, well, we observed that this ring, first of all, this coordinate ring here, is a Noetherian ring, which is exactly a ring which contains no infinite increasing chain of ideals. So this one here is Noetherian, and then it's a general result that the quotient of a Noetherian ring is again Noetherian, which shows that AX is Noetherian, and therefore there cannot be any such infinite increasing chain of ideals. We get a contradiction. So It's not a coincidence that on the topological side, these spaces are called Noetherian if they don't have strict decreasing sequence of subsets, because under this correspondence between subsets and radical ideals, we get from this infinite increasing chain of ideals. So that finishes the proof, and it shows that all the affine varieties will be Noetherian. And we could now do the entire chapter here, just restricting to X being an affine variety, and then show things like the irreducible decompositions. But in fact, it's nicer to do it with as few assumptions as necessary, X being Noetherian, because then later we can also apply it in other settings when we start generalizing from the setting of affine varieties. One immediate consequence is that it will be important to not just consider the affine varieties itself, but also, for example, open subsets of them. So for example, sometimes you don't just want to look at AN itself, but the open subset where you remove a variety. So for example, where you remove a single point. That's certainly a nice space. And it turns out these are also Noetherian. And that's a kind of general proposition, which we can see that if you have a Noetherian topological space and any subset of X, then it carries itself a structure of a topological space with the relative topology. And the claim is, with this relative topology, A is then also Noetherian. So if you go to a subset, this property of being Noetherian is preserved. In particular, if AN is Noetherian, then also this open subset here would be Noetherian. Okay. For the proof, well, we just apply the definition. Assume we had a strictly decreasing sequence of such closed subsets of A in the relative topology. Then next, we plug in the definition of relative topology. It says, well, being a closed subset in A just means there exists a closed subset in the bigger space X, such that AI is the intersection of this closed subset Xi with our subset A. Now we have gotten ourselves from this decreasing sequence of subsets of A, we have gotten a sequence of closed subsets Xi. Now we would like to claim, well, just take X0 subset equal X1 and so on and so forth. But the problem is we don't really have control over whether X0 contains X1, because a priori we just know what these subsets do on A. But we can kind of by hand modify the sequence, ensuring that we get inclusions. And for that, we can start with the set X0, and then it certainly contains the set X0 intersected X1, and this contains the set X0 intersect X1 intersect X2, and so on and so forth. So these inclusions are okay because we just keep on intersecting with more and more sets. Furthermore, because all the Xi are closed, also these finite intersections of the Xi remain closed. So we have already gotten ourselves now, with the slight trick of taking successive intersections, we have gotten ourselves a decreasing sequence of closed subsets of X. The only thing to finish the proof, now we would like to claim that all of these are strict, because then we would get a contradiction to X being Noetherian. To see that they are strict, what we do is we look at one of these things, so the intersection of the first, I guess, I plus 1 sets here, and then let's intersect everything with A. So basically in this sequence of inclusions, basically intersect every term with A. And then we just see, well, if we do the intersection of this last thing, xi with a, then by definition, this was exactly how we chose them. We get ai. And now, well, ai, this lands somewhere in this chain, and then we see it's contained in all of these things. ai is contained in ai minus 1, ai minus 2, and so on. And these things are contained in the xi minus 1. Again, because of this property, you see ai is contained in xi, ai minus 1 is contained in xi minus 1, and so on. So from this observation, we see, so taking this intersection, we have reduced to ai, but now ai is contained in xi minus 1, is contained in xi minus 2, and so on, all the way up to it being contained in x0. And that's good because it means then all these other intersections don't do anything, because this thing is already contained in each one of them. And so nothing changes anymore after this first step, and you just get ai itself. Well, that's good. So where were we again? So we had this sequence of inclusions. Now we intersected every one of those members with a, and then we see we get exactly this sequence of strict inclusions. And now, if one of those things here wasn't a strict inclusion, for example, if this thing here was equal to this, then after intersecting with a, of course, this intersection with a is also equal to this intersection of a. But this would give us a contradiction, because we see here this was a strict inclusion. And so after intersecting with a, we intersecting with this, we get a strict inclusion. So this cannot have been an equality. This would give a contradiction. And so, in fact, all of these things need to be strict. And we have our contradiction to X being Noetherian. So looking back at the proof, what we just did is start with the strictly decreasing sequence here, and then from this obtain a strictly decreasing sequence in the bigger space. And then the rest is just kind of checking small details. Okay. So that's certainly a useful thing in mind, and to keep in mind. And that's one of the reasons why it's nicer to formulate the entire section now in terms of Noetherian topological spaces. Okay, and then we can come really to the main result of this section here, which is the irreducible decomposition. So it says every Noetherian topological space X can be written as a finite union of spaces x1, union x2, and so on, union xr, where all of these are non-empty and irreducible closed subsets. And in general, this thing here would not be unique for stupid reasons. Like, for example, you take x1, union x2, and so on. This would be a second one, which has one more member, but you didn't really do anything because you just repeated one of the terms. If you assume that this decomposition satisfies that none of the xi is contained in a different xj, for I not equal to j, this would exclude this proposition of taking 2 times the same, for example. So if none of them is contained in the other one, then the claim is these x1 up to xr are unique up to permutation, so up to changing the ordering. And well, clearly, if you have any such decomposition here as a finite union, well, either there's no such inclusion and then you have the unique one, or if xi is contained in xj, then of course you can just remove it from this thing without changing the union. I mean, if x2 is contained in x1, then you can just strike this term out and you still get the same union. So starting from any decomposition like this, you can always go to one such minimal one. And so these xi are then called the irreducible components of the space X. And in that example, which we had around, we really see x1 and x2 are the unique irreducible components of this original affine variety X. And in particular, before we go to the proof, you then see, of course, that if you take X to be an affine variety, then you find such an irreducible decomposition. Okay. For the proof, there is a kind of boring case when X is the empty set, then all of this is fine. You can take R to be 0, and then basically you say the empty set is the empty union of things. That's fine. So this case is done. The only reason why we mentioned this is that then in the rest of the proof we can assume X is non-empty, which is often nicer. So let's say, first of all, we proved the existence of some such decomposition. In the second part, we proved this uniqueness up to permutation. So assume that that X was not a finite union of irreducible sets. We do a proof by contradiction. In particular, as the first consequence, we see, well, X cannot be irreducible itself. Otherwise, you can take R equals 1 and then X is equal to X1. That would be a contradiction. So X is not irreducible, which means it must be reducible. So you can decompose X as a union of X1 with X1 prime, where these are both strict closed subsets. So here we start seeing like where will these strict closed subsets come in. And now, I mean, before moving on with the formal argument, let me just kind of give you the idea. So we started with X and then we decomposed it as a union of X1 and X1 prime. And then we kind of iterate this argument. If one of them was not a union of finitely many things, which is guaranteed because we assume that X is not such a finite union, well, then we can decompose it further and further. Some of these chains would stop because, well, maybe X1 is decomposed into these things and this is irreducible. But the fact or assumption that this is not a finite union means it cannot stop at some level, because if it stopped at some level and we had only irreducible things left, then these finitely many things on that level would give us a union of X. And so this argument shows that more or less this recursive procedure cannot stop. And then you just have to see that starting from X, you can navigate through this tree and you find an infinite chain, which gets smaller and smaller in each step. This gives a contradiction to X being Noetherian. So that's the rough idea. And to make this idea precise, well, we have in the proof, we were at this stage, if X is irreducible, then we have decomposed it into two things. Now, if both of them were a finite union of irreducible sets, then, of course, also X would be a finite union, because you can take the finitely many things from here, finitely many things on here, and this would cover X. So it cannot be the case that both of them are finite unions of irreducible sets. So let's say X1 is not a finite union of irreducible sets. And then we're in business, because then we are in this first part. So repeat the argument. And then we find a strict inclusion X2 inside X1, such that X2 is still not a finite union of irreducible sets. And so we continue in each step, and this kind of chooses this path in this tree, and you find an infinite sequence, which gets smaller and smaller in each step. This gives you the contradiction to X being Noetherian. Okay. This is the existence part. And now we need one more clever argument to show that if you have the assumption none of them is contained in the other, then this is unique up to permutation. To show something like this, well, you always have to assume that you're given two different decompositions. So let's say X on the one hand is this union of R closed sets, and it's also the union of R prime closed sets. where all of these xi and xi prime are irreducible, and none of the xi is contained in any other different xj, and none of the xi primes is contained in any different xj prime. What we need to show is now that both r is equal to r prime, the numbers are the same, and then that there's some permutation of this side which gives you this side. Okay, and what we do is we kind of start on the left side, so consider I0 from 1 to r corresponding to one of the things on the left-hand side. Then this xi0 is, we now start forming a covering of this. So xi0 is of course the same thing as xi0 intersected x. Everything lives in x. And then x, here x is the union of these things. And so somehow you can replace this by the union of the xj prime. And then A intersected union is the union of the intersections. So somehow you see here xi0 is xi0 intersected x1 prime, xi0 intersected x2 prime, and so on until this one here. So now we have covered xi0 as a union of things, and all of these, because these are closed sets, these are still closed. Then, using that xi0 is irreducible, I claim there must be a j0 such that this actually equals one of these terms on this side. So recall that when we introduce the notion of being reducible, or let's say when we discussed what it means to be irreducible, we said that the space is irreducible if when you cover it with two closed sets, then it must actually be equal to one of them. And so there's a slight generalization. If you apply this definition several times in a row, you can also show if an irreducible space is a union of finitely many closed sets, then it must be equal to one of them. Okay, so we use this here, and so we see xi0 is equal to one of those intersections. But well, xi0 being equal to xi0 intersected something means that xi0 must be contained in this something. So xi0 is contained in one of the terms on the right-hand side. This is what we showed so far. Each one on the left-hand side is contained in one of the other things on the right-hand side. But now, well, the situation is symmetric. So we can now take that one in which it is contained, and by the same argument applied in the opposite direction, this will be contained in one of the things on the other side. So there exists I0 prime, such that the xj0 prime that we found is contained in xi0 prime. And now we have kind of two inclusions. This one here was contained in the xj0 prime, and this is contained in the xi0 prime. But now, well, we started on the left, we went to the right, and then we went back to the left. So this one on the left is contained in another one on the left. But by our assumption here, none of these things is contained in any other one, which means it must be contained in itself. So this is the only possibility that I0 is equal to I0 prime. And so this in here is actually equality. And so if you have a chain of inclusions such that the first entry is equal to the last entry, then all of the inclusions must be equalities. And so in fact, you see that this is equal to one of the things on the right-hand side. So taking a step back, what we showed, any xi appearing on the left is actually equal to one of the things appearing on the right, and vice versa. And that means the set of these closed subsets appearing on the left is contained in this set, and vice versa, this set is contained in here. And then you have kind of two inclusions, and this means actually two sets must agree. And so up to ordering, this decomposition here is unique. Okay, so this was a proof which had kind of several ideas which you needed to input, but basically, at least on a theoretical level, it gave you some idea how you could construct such a irreducible decomposition. And the next videos will explore this further.